list, we have two sorted lists, and you essentially take a merge sort of those. And then that essentially is what every node will see, some ordering of those two, basically. And certain nodes could actually fail. Some of these sequences are, think of them as computing something, right? So certain, if all the nodes that are looking at this order, they agree on one ordering, that ordering is essentially becomes your blockchain. Okay, so there are many ways to you do consensus. One is, I typically use the word democracy, which essentially means you do typical consensus like, you know, your Paxos, or you pick any of your classical consensus. They are very democratic in the sense that when majority of them have the same sequence, we sell that is the actual sequence that everybody agrees on, or majority of them agrees on, and then we essentially construct a block and then put them in a blockchain. In fascism, which essentially is one person determines what that sequence is, and typically if you look at Bitcoin, the person who has the most power, which is essentially ability to solve a crypto puzzle, has the ability to say, hey, that is the block that I am going to consider as block, and everybody has to follow that fascism rule, right? So the notion of agreement, if you look at the computing model that I early on defined, the main difference between the Bitcoin world and the classical distributed system is this whole notion of solving this crypto puzzle. And Satoshi essentially came up with this idea and actually solved some fundamental problems in distributed systems. One of them classically is the Sybil attack, right? So if you have the ability to solve something, you're going to expend some money to it. And if you notice right now, much of the Bitcoin world, they essentially use solving this crypto puzzle. And then we also want to handle, how do we handle these failures? Failures, there could be many types of failures, but we usually classify them as two types. One is called fail-stop failures, which essentially means the node doesn't respond. And the other one is malicious, are called Byzantine failures, where a node behaves maliciously. I'm not going to go into the details of those. Those are not actually important for the discussion. I'm going to pause here to see if there is any questions, Susan, you think that I should be able to answer now.
I see no questions in the chat yet.
Okay. So let's look at this consensus as a computation. So let's look at this consensus as a computation model, right? So think about, we have a sequence S1, S2, S3, and T1, T2 that gets submitted, and every node in there performs certain computation or computes some function, and that function is y equals f of x, where x is your sequence that is actually coming in, and y, you can think of them saying that, hey, I agree with that sequence, which essentially means if majority of them agree that sequence, then that's essentially what we have. And if they don't, then they essentially agree on a different sequence, basically. So in some sense, every node is performing some kind of computation. Or, for example, they actually solve a puzzle or attempt to solve a puzzle. They did not solve a puzzle. They can actually do any computation at those nodes. And all they need to do is or majority of the node in the democracy case, or in the fascism case, one person who has the power will essentially say, hey, that's the block I'm going to say, and that is my y that I'm going to agree on, or f of x, which is essentially here. So we can actually twist this around and slightly modify the topology of that computation model I just mentioned. Think about these S1, S2, S3 as a sequence that is being submitted to some network that is organized in this fashion. And then we have layers of these networks themselves. Rather than they're actually talking to each other, every node talking to every node, we can essentially say, hey, I'm going to construct a topology of these nodes where they only talk to based on the topology itself. And that topology essentially defines how the computation is actually progressing here itself. So now imagine I have these S1, S2, up to T, whatever the sequence. At the end, we have what is called an accept and a reject state, which essentially tells you what is the legal or illegal sequence that is admissible from a computation point of view in any consensus model. And that consensus model, you have to kind of parameterize themselves. And some nodes will fail, which is fine. And that's essentially what we are doing here is we have a sequence x1, and then you have a function which computes that, which does some computation, and then we have the output of that is either accept or reject case. So now if you kind of look at this, this is nothing more than a feed forward, backward. You can think about any neural networks or deep learning networks. So I'm going to kind of take you through this journey a little bit more. The differences that you will see here is in neural networks, every edge has some weights. And in the blockchain world, those weights are nothing more than the consensus algorithm itself in some sense. How the nodes propagate the sequences for them to agree upon themselves. In some sense, if you look at neural networks, they're actually propagating partial information across the network, and together all of these nodes agree on the final result has to be either accept or reject, which is essentially what you do even in blockchain world. In some sense, you can see the weights where we learn and the consensus in blockchain are equivalent in some mathematical sense, which I haven't figured out what that mathematics is yet. I'll talk about some of those things as we proceed, okay? So just to give you a brief idea of how deep neural networks kind of people start thinking about them is typically they start with some kind of a linear transformation, like matrices. Typically, if you look at some of the classical machine learning, they tend to use matrices, and some people tend to kind of use, go to the next level, which are networks and tensor products. So the most of all the matrix stuff, most machine learning, I would say more than 30 to 40% of the majority of machine learning falls into this category of matrix decomposition or factorization, which essentially people tend to use, if you look at recommendation systems and others, so they essentially do what is called matrix factorization. Or even if you look at, in some sense, deep neural networks, what they are essentially doing is matrix factorization, but in a much more layered way, okay? Tensor are nothing more as an extension to matrices. Even though tensor and matrix are two different, mathematically they are two different, you can essentially construct some nice properties, but not in matrix world, but you cannot construct them in the tensor world. The interesting thing with tensor is you can actually convert all of these tensor and matrices into this word, what we call as monoidal categories. I don't want to go into the details of theory, and you can actually use to construct your mathematical properties. And many of these mathematical structures that fall in, for which we want to do certain computations, you can actually construct them using these monoidal categories, and they actually give you a nice graph properties. And those graph properties is what I'm actually interested in here. That's essentially what I introduced. So I'll give you a little bit more examples that people who are familiar with classical machine learning. For example, think about belief network or Bayesian network. In the neural network world, they also have deep belief network. That is nothing more than Bayesian networks that you see in there, right? So typically, if you look at this, a belief network or a Bayesian network would look like something like this. You can actually do factorization on those, and those factors that you see, F and G, are essentially used and to construct your conditional distribution. For example, naive Bayes, you essentially have a one hidden variable, and then the rest of the nodes are generated because naive Bayes is a generative system. So why am I talking about matrices, belief networks, all of these? These are all essentially what I call them as submodels of certain deep neural networks, and think of them as different consensus algorithms in the classical blockchain world. So one of the other things, there's only 3 things that you need to know in deep neural network. This is a 1-page deep neural network introduction. So if you look at any deep neural networks, they have essentially 3 things. One is the input, next is the hidden, and then you have the output. So the problem in deep neural network is, given any 2 of these 3, you have to find the third one. That's it. Almost all deep neural networks that I am aware of, maybe there are things that go beyond this, essentially the problem kind of, you can summarize them as you have inputs, you have weights, you have outputs, and the problem that you typically work on is you're given 2 of them and you find the third one. So what does that actually mean? What are the 3 things? Suppose you're given the input and the weight, you actually find the output, which is essentially typically called as discriminative analysis or prediction in some sense, right? If I give you the input and the output, you have to find the weights, and those are the learning models. People, when they build learning models, they essentially, for example, supervised learning or otherwise, they essentially do that. And the third one is you're given the output and the weight, then you have to find the input that actually generated that output. Those are typically the generative models. So things like deep belief network fall into these generative models in the classical deep neural networks. And discriminative ones is you think about your classical, recurrent neural networks or convolution networks. They essentially fall into one and two of those two categories. Okay. So let's look at this learning as a computation. I'm hoping I'll finish in about 5 to 10 minutes. So as I mentioned, we have a function y equals f of x. The learning is essentially estimating f. Remember, we are focusing on learning. That means you're given the input and the output. I need to figure out what is that function is, or estimating those functions. Typically, in machine learning, you have to have these functions to be regular. What are those regular? Typically think of them as rational functions. In some sense, they don't have sudden jumps. They could have jumps, but you can essentially convert those jumps using certain polynomials into rational functions, basically. In some sense, most machine learning techniques, the classical machine learning techniques, typically you start off with something like a rich function. Think of these rich functions as, for example, in terms of linear machine learning, like linear regression or linear classification. Once you construct your rich function, you can essentially determine what is your error. Error is essentially the limit as you increase the number of your inputs, and that tends to go to 0. Okay, so typically, for example, in the piecewise linear approximation, these functions are linear function. You can actually extend that to any polynomials. Then you construct, rather than having these rich functions as linear, piecewise linear, you can actually introduce them as polynomials. And these polynomials essentially gives you much more smoothness, but they also give you what are called the second order and the third order differential, because the classical rich function, they're usually first order differentials, not second order and third order, because that's why you get linearity there. But here you can essentially construct polynomials. These polynomials, why am I interested in this polynomials? I'll soon talk about that, for example. So now let's look at this consensus as a learning. Now you're given y equals f of x, but unlike in classical machine learning, we have sequence of transactions, and the output is either legal or illegal. So can we use convolution network or convolution neural networks to address consensus as a learning? The answer is no, because convolution cannot handle sequence of transactions, because you have to have a fixed network before you can even start thinking about learning from a convolution network point of view. And so the fallback to that is essentially the famous recurrent neural networks. If you think in terms of long short-term memory, it's become very popular. Essentially, what will happen is, if I give you a sequence of transactions, what are the number of possible merge? If I give you 2 possible merge, right? It's essentially, in fact, it's usually a huge number. And recurrent neural networks, essentially the idea is you have a function that unravels itself. That means the output of the current state is actually fed back into the input. And then you think of them as like Markov chains, right? You can essentially think about the next page essentially gives you a quick formula for this. Because recurrent neural networks are dynamic state evolution and depends on the input and what it did in the past, including the current state, that t plus 1 could be anything in the past, like any recurrence network. So typically these recurrent networks, think of them, if you understand hidden Markov model, it's nothing more than hidden Markov model plus distributed state, where states are actually distributed in them itself. So again, you can actually construct these as functions g of s, where g of alpha that you see, we can actually handle any functions that are actually regular in this case, and then can easily handle variable and structure. That's why we have recurrent neural networks will be a better fit model for modeling consensus as learning. One final thing that I wanted to kind of take you here, even though recurrent neural networks are Turing complete, which essentially means they can do any algorithmic task or they can actually simulate arbitrary procedures, but it's not very convenient to handle such kinds of computation. Think about the smart contracts that exist in blockchain, those smart contract could be any arbitrary procedures, right? I mean, for example, you have to do certain computation there. Yes, you can actually construct a complex recurrent networks to do that. But interestingly, there is a paper that came out a couple of years ago where they actually combine recurrent neural networks with Turing machine, which essentially becomes what is called a recurrent or a Turing neural networks. As you know, Turing machine is nothing more than finite state machine plus an infinite tape on it. That essentially makes it, Turing machine. So Turing neural networks, think of it as nothing more than a recurrent neural network plus addressable memory. Keep in mind, the Turing neural network, in terms of computation, I mean, in terms of expressiveness, when what you can actually compute is exactly same as recurrent neural network, but it gives you the convenience of these addressable memories. But it actually brings one thing which is actually very interesting in Turing, which actually is interesting for me personally, is these Turing neural networks, they're actually differentiable computers. What does that mean? You can actually train those Turing neural networks. Unlike classical Turing machine, we have these computers that are actually differentiable. Why do I need those differentiables? Is because I can actually do computation in applying classical machine learning techniques, or so that I can think like training and things like that, right? So right now, I haven't, I have more details in my notebook. So I'm kind of introducing this concept of what I call as differentiable consensus, using concepts from these Turing neural networks. I don't know what it actually means. Essentially, if you look at consensus that is currently happening, most consensus these days, any practical consensus, they don't essentially follow deterministic consensus. They are all converging them itself into stochastic or probabilistic consensus. But we have to also make sure that it is actually differentiable. What does that actually mean in blockchain world? People talk about something called eventual consistency, which essentially means eventually two people will agree on something, but that agreement, we need to be able to prove convergence of that. If you look at something like PBFT, the classical original PBFT, it never converges. It can take infinite amount of time for it to actually get consensus. We want to avoid such those kinds of computation. Those are, I call them a singular computation, right, which will take forever. But if you actually ensure that the algorithm that you're developing for consensus are differentiable, which essentially comes down to something called differentiable consensus, we can essentially construct consensus as a learning procedures. I'll give you a couple of maybe two examples, right? Imagine that you're in a jury duty and you have a set of people who are sitting together to determine whether a person is guilty or not. You can actually model both the jury duty as a machine learning problem and also as a consensus problem. But so that the underlying, at the end of the jury procedure with finite amount of time, they have to come to one of the two, either guilty or not guilty. The same thing, when you want to create a PowerPoint chart for your CEO, you have a bunch of people sitting in a room trying to construct a PowerPoint chart. The output of that PowerPoint chart is what we call as a block in a blockchain, but that has to come in certain finite time. You can't take an infinite time. That's why you need what we call as differentiable consensus. What we need here is we need experimental research people and mathematical people coming together. You have to lock them up so that they can actually build this, what we call as a real world-class developers and world-class mathematicians. They can actually do a lot more magic than you keep them separately, right? So I'm actually exploring all of these using concepts from algebraic topology and algebraic geometry and category theory and differentiable geometry. So I'm going to pause here, and I think I'm done with my presentation. I'm willing to take any questions, Susan.
Thank you. That was great. I do see one question in the chat from Kautar asking you if you've come across a specific use case where the function for blockchain consensus can be modeled as a neural network.
Jury duty.
Jury duty. Excellent. The one you've mentioned. Okay.
Anything else?
Any more questions, anybody?
Okay.
Thank you so much, Sreedhar.
Oh, we see another message. Oh, can you talk about, there is. Can you talk about how a cryptocurrency blockchain differs?
Okay, sorry, can you repeat the question?
Can you talk about how a cryptocurrency blockchain differs?
Differs from what?
I guess from just a blockchain that isn't about cryptocurrency.
Okay, so I
think anonymity perhaps might be one difference.
Yeah, but to me, there's no difference between Bitcoin world and the Hyperledger Fabric or any other blockchain, because they're all part of same, what I call them as distributed systems, right? The main difference is actually how you actually model the consensus, basically. The consensus in Bitcoin world is typically a probabilistic consensus because you solve certain crypto puzzle there. You can essentially introduce probabilistic consensus even in the Hyperledger Fabric world. For example, Honey Badger to some extent is actually a probabilistic consensus there.
There are now lots more questions. Thoughts about use for smart contracts. Are you thinking of applying learning to tackle attacks on nodes to influence consensus?
So I'm okay. Those are not related to this particular talk in general. So my goal in this talk is essentially show what is the difference between consensus and learning, and if you think of how can we use, why am I actually doing this? It's not just I'm doing this for fun. Yes, to some extent I do this for fun. Is essentially, if you look at deep learning, they have developed a lot of mathematics behind it. And if you look at distributed systems, they have developed a lot of mathematics behind it. And I see a lot of symmetry between the two worlds because I worked in both worlds, right? I work in both worlds, basically. So for me, all of this falls under the category of computation in models. So my question is, when we are actually thinking about consensus, in terms of coming up with new consensus, can we come up with consensus that actually converges in a mathematical sense? What are those consensus? Those I consider them to be what I call them as differentiable consensus. Don't come up with consensus like PBFT. It would never converge in some corner cases. We don't have to go and figure out what the protocol should look like. If you kind of model these consensus as mathematical objects and you have certain, for example, complex simplicals in topology, simplical complexes in topology will tell you what kind of things can you actually do or not do. Maurice Hurley has done excellent work in that space. If you guys go buy his book and try to learn his algebraic topology methods for distributed systems for proving undesirability, you will notice, right? So in some sense, my goal here is doing mathematics behind the scene where I can bring these two worlds together, basically.
Thank you so much, Sreedhar. I think we can sort of stop the speaking portion of the call. If you can find your way to the chat, you can answer people and see all the nice thank yous they're giving you. You can stop sharing if you like, Sreedhar, okay, and then go and look in the chat.
Okay.
You can.
I have a meeting that I need to attend at 11. So is there any way that I can respond this in a different way than?
Yes. I'll send you the chat and you can respond in another way. But thank you so much. And thank you, Padma, and thank you all the volunteers who helped make this happen.
Thank you.
Looking forward to the exciting talk next week, same time, same place.
Okay, thank you very much.
Susan, we're closing the meeting, right?
Yes, but I'm copying the chat, although it does save it, but I'm also copying who attended, and then I'll close the meeting.
Okay. All right. Thank you. Thanks,
yeah.
everyone.